We are creating a series of videos on how to create a compiler. To that end, we will be using Flex for lexical analyzer. We will use Bison for syntax analyzer and semantic analyzer. And finally, we will use a very important framework known as LLVM to produce intermediate code, to do code optimizations, and finally to translate our intermediate code to different platforms. Before we start creating a compiler, we have to describe a programming language for which we will be developing a compiler. I wish that my student can learn to create compiler without much complications. So I want to write as less code as possible. Therefore, I have decided to create compiler of two different languages. First, I will create a compiler for a language which I called Simple C. Subsequently, I will create compiler for a language which we call Simple C. So Simple C will be a small subset of C language which will be only used to create a calculator. So we will have instructions like C equals to 5 plus 7 semicolon. We will have D is equals to 5 times parenthesis start 9 divided by 3 close of parenthesis semicolons, and we could have instruction like E equals to C minus D. By default, all of our identifiers will be of type double. In Simple C, we will have two built-in print instructions. One is print s, that takes a string and print it. Second instruction that we have is print d, that takes a double identifier or a double literal and print that identifier or literal. Let's discuss that what kind of keywords and tokens our language Simple C will have. In Simple C, we could have identifiers, and a name of identifier will follow C convention. We could also have double literals like 3 or 3.97 and so on. We could have different arithmetic operators like plus, minus, divide and multiply. We must have equal to operator because we have to write like E equals to C minus D or D equals to 5 times something. Furthermore, we will have comments, but in Simple C we will only have single line comments which start with double slashes, just like C language. We will have two built-in print functions as described above. One will be print s, that will print strings, and other one will be print d, that will print doubles. Finally, we will have semicolon, we will have start parenthesis, and we will have end parenthesis. So that's it. This is all we will have in our language Simple C. Once we created a simple compiler for Simple C, then we can learn more about how to create compiler using a language Simple C. In Simple C, we will have if conditions, we will have if-else conditions, we will have while loop, and we could have multiple functions. In the next 3 to 5 videos, we will be developing Flex, Bison and LLVM code for our language Simple C, and afterwards we will work on Simple C language. In this video, let's develop the Flex specification and then test our specification on the code of Simple C. So let's start with creation of flex specification for simple C. In order to create my flex specification, I open the terminal and I create a new directory with the name SSC. This directory will have the complete compiler for my programming language. But in this video, I will be creating the flex program for our simple C language. So let's start with creating ssc.l file. We know that the extension of the flex file is usually .l. In my flex file, there are 3 sections as described in the previous video. Each section is separated by double percentage sign that is the end of a section marker. In the first section, we write definitions. In the second section, we write rules, which is obviously the most important section of this file because rules identifies different token of our source file. And in the final section, we write C or C++ code. Furthermore, we also write our main program to test our lexical analyzer in this section. So let's start by writing rules in the middle section, and we will populate the first and the last section as we need during writing of the rules. Note that the order of writing rules is important. We should always write rules about keywords first. In our simple language, there are only 2 keywords. First keyword is print D. So I have to write a regular expression that match this print D keyword. The regular expression that can do that is double quotes print D. Even these double quotes are optional, but I like to write them always. After this regular expression, I have to give some spaces, and then in the curly brackets, we write C code. This C code will be executed whenever my keyword print D is found inside the source code of my language. So in the C code, I simply write return talk print D. This talk underscore print D is an integer constant that will be declared in a header file ssc.tab.h. So let's first include that header file. We will create that header file later on, but we have to include it maybe right now. So we go to our first section of file, which was the definition section. In this section, we write percentage curly brackets and percentage end curly brackets. And this is the part where we can write C declaration. Here I write include ssc.tab.h. Note that later on, Bison will create this header file by itself, and we don't have to write this header file by ourselves. But in this video, because we are writing a standalone lexical analyzer, we will be creating this header file ourselves. We are done with the first rule. Now let's write the second rule of second keyword. In this rule, we have to identify keyword printS, and the regular expression double quotes printS do that. Then we will provide some spaces, and in the curly bracket we will write C code that will be executed upon finding string printS in the source code. And here I will write C code of return talk underscore printS. Once again, this talk underscore printS will be declared in the header file ssc.tab.h that we will create later on. So we are done with both of the keywords of our simple language, or rather simple language. So now we can write regular expression for identifiers. In our language, an identifier starts with English letter. So I write bracket start A to Z, that means any English letters from small a to small z, and then I will write capital A to capital Z, that means any English letters from capital A to capital Z, and then I close the bracket. And this is the regular expression for the first letter in my identifier name. Now I have to write regular expression for the rest of the letters in the identifier. After the first letter, the second, third and fourth and so on, letters of my identifier can be composed of English letters. So I write once again small a to small z and capital A to capital Z, but the letters other than the first letter can also be numbers. Therefore I write 0 to 9, and also the letters other than the first letter can also have underscore. So I finally write here underscore, and then I close bracket. And because this rule has to be applied multiple times, because we can have multiple letters where this rule has to be applied, so I add a star. The star refers to that this rule has to be applied either 0 or many times. So the first rule is only for the first letter and it has to be applied exactly once. But the second rule of my regular expression has to be applied 0 or many times, because it is for the second and for all the letters that comes after the first letters. So now once again we provide some spaces, and then I write C code that will be executed upon finding an identifier in the source file. I write here return talk identifier semicolon. Once again, this value will be returned whenever we find an identifier in our code. But where we will store the name of identifier. This talk identifier will always be returned, even when name of my identifier is ABC, or if name of identifier is X, we will always return talk identifier. That means we have found an identifier. I have to store the name of my identifier somewhere. To that end, I write YYLVAL dot identifier is equals to YY text. Let me explain what this piece of code implies. First of all, YYL value is a union that will be created by Bison, but for this video we will be creating that union by hand, and we will be writing that union definition in ssc.tab.h that we have to create later on, and dot identifier is an element of that union obviously. But this yy.text is a built-in variable of flex, which is of type character star, and this variable store the current lexeme being processed by the lexical analyzer. So if the current lexeme is a print D string, that will be stored in YY text, and if the current lexeme is print S, it will be stored in YY text. If the current lexeme is a name of an identifier, maybe I, that will be stored in YY text. So we say that whatever in YY text, store it in the element of a union. That we will declare later on. Now here I want to emphasize importance of the order of rules. If I describe rules of identifier on top of rules of keywords, then lexical analyzer will match print D with the rule of identifier. It will also match print S with the rules of identifier, because our rules does not say that print D cannot be an identifier. Our rule does not say that print S cannot be an identifier. And when it match print S and print D with an identifier, it will not match print S and print D as a keyword. But if I write my identifier rule below the rules of keyword, then my lexical analyzer will first match with the rules that is coming above it. That means my lexical analyzer will first match keywords. When a LLVM does not match with the keyword, only then it will match with an identifier. Therefore, our rules for keyword must come first, and the rules that have higher precedence must come first. Next, we have to write rule for double literal. A double literal could be an integer. So let's first write the definition of integer. Integer could be a sequence of multiple digits. Therefore, I have written regular expression of 0 to 9, and at the end I have written a plus. Here plus implies 1 or more. That means I could have 1 or more digits in my integer. Recall that static implies 0 or more, whereas question mark implies 0 or 1. So we use question mark for things which are optional. And the second part of my double literal is optional. The second part of my double literal is the decimal, and integer comes after the decimal. After the end of the second part, which is optional, I write a question mark. So my regular expression for a double literal is almost complete, except that I have to use an escape character before my decimal point. It is because a dot has a special meaning in the regular expression. Dot implies all the characters except \n. And here we don't want to use all the characters except \n. We want to use only a specific character, that is dot. Therefore we write escape character, which is \, before dot. That's it. So this is the regular expression for my double literal. Now, after some spaces in the curly brackets, we have to write C code that will execute whenever we find a double literal in our source file. In this code, I write return talk double literal. This integer will be returned to Bison and to LLVM whenever we find a double literal in our source file. However, I have to save the value of that double in some variable so that we can use that value also. To that end, I described a new element of my union, and I write yyLvalue dot double underscore literal equals to yytext. Next, I have to write rule for string literals. A string literal starts with a double quote, but here we have to specify this double quote is not a regular double quote that we have used in our regular expressions such as print d and print s, but this double quote implies that this is a character which is part of the regular expression. Therefore we have to write escape character before the double quote. In between two double quotes we could have any character but a double quote. This # sign implies anything but whatever follows the # sign. That means any character but double quote. And we have a star, that means in between the two double quotes of string literal they could be multiple characters. And that's it. Next we have to write C code that will execute when we find a string literal in our source file. I write return talk string literal. So I will return a integer whenever I find a string literal in my code. Furthermore, I will also have to store my string literal in the union. So I write yyLvalue dot string literal equals to yytext. And that's the end of this rule. The next rule is about comments. In this language, comments followed two front slashes. So we have to write 2 front slashes as our regular expression, and then in the portion of the C code we have to write a semicolon. That means return nothing whenever you see 2 consecutive front slashes. However, front slash also has a specific meaning in the regular expression. Therefore, we have to use our escape character, which is a backslash. So we have to write a backslash, front slash, a backslash, front slash, making 2 front slashes indicating a start of a comment. After 2 front slashes, we want to ignore whatever written in that line. To that end, we have to write a dot, because a dot represents all the characters but backslash n, followed by a dot will be a star, because dot is a single character and we want to repeat the effect of dot multiple times till the end of the line. So we write dot star, and that's it. This is the rule for our comments. After comments, we have to write a rule to ignore all the spaces, new line characters, tabs, etc. Finally, we have many operators in our source code that we need to identify. We know that our token is ID and LLVM pair. For those operators, we can return their ASCII code as their ID. We could then use those operators as it is in Bison and in LLVM. Hence, in the regular expression, I have ORed different operators together, and in the C code, I return their corresponding ASCII codes. At the end of rules, we must always have special rules about errors in lexical analyzer. In our case, we have a dot as a regular expression. This dot implies that all characters which are not matched by any of the valid rules written above will be matched by this dot. Upon matching with the dot, we return a lexical analyzer error. In the C code, I have written a YY error function which returns a error. I will write the definition of YY error function in ssc tab.h header file. Then I have written an exit instruction, as I want the program to exit at the first error encountered. That's it. We are done with all of our rules. However, if I run this flex specifications, then I will not see any output because there is no print instructions anywhere. So let me add some debug print instructions so that we can see our progress as we run this file. I create a C macro for a debug function, which I believe is the optimal approach. Within the debug function, I initially print the current line number of the source file followed by the current token in the format of token ID and LLVM. Flex provides a built-in variable YY line number which records the line number. To activate this variable, we need to include %option YY line number in the definition part. of the flex file. Subsequently, I call the newly created debug function in the C code of every rule so that we can see the output while the lexical analyzer process our source file. Next, I have written the main function to test our lexical analyzer. In the main function, I open a file based on the input arguments and stores the file pointer in variable yyIn. yyIn is a built-in variable of Flex used to read the source files. In case an argument is not provided, then yyIn is equated to the standard input stream, which is stdin. Now the most important function of Flex that processes all the rule is called, that is yylex. This function will return the value of current token, but will return 0 if the end of the file has been reached. Therefore, my while loop terminates whenever yylex returns a 0. We are almost done. The only thing left is to create the header file and then run our test program. I need to add an option no yyWrap, otherwise my code will not compile. This is because yyWrap is a function used to read multiple source files, and you have to either provide implementation of that function, or in case you want to read only a single source file, then you must include the option no yyWrap. Now over to the header file. In the header file, I create an enum where I list all the token IDs. So I copy each token ID from my ssc.l file and I add those token IDs in the enum. I am careful not to use 0 as a token ID, as it is reserved for the end of file. Subsequently, I create a union in the header file with the name yyLValue. The union will be used to store values of different tokens. Note that this union will take memory equivalent to its largest member, so it is a good design practice to use union here instead of a structure. I want to store the value of token double literal in double variable instead of a string variable. So let me use ASCII to float function to convert character string to a double. Note that this header file will be later on created by Bison, but we need to create it now so that we can test our lexical analyzer without having to use Bison. I also have to write the definition of yyError function in the header file, which I have done, and that's it. My header file is complete also. The next step is to test everything. In order to run it, I write flex ssc.l. Flex has created code of a lexical analyzer in a file lex.yy.c. To compile the lexical analyzer, I write clang lex.yy.c. Unfortunately, there is an error that in my enum I forget to add a equal to sign. So I quickly open my header file, add the equal to sign, and then our code now runs without any error. It is able to process all the tokens correctly, and that's it. We are done. Now I will start working on the next video so that I can create Bison for our simple C language. So stay tuned.